Thank you. All right, cool. Then I'll just head off. So first of all, I'd like to thank the organizers for having me. It is a pleasure to be back here in Santa Barbara, and I am also very happy in filling in this this spot, simply because we all heard from Stephen Wilson a lot about CVS in the morning, the cesium, vanadium, antimony compound, and also transporting Kagome nets in general, so that it would be, it helps me that I can skip some of the introduction and talk about some other things. Now, I'm very happy also that the conference is with and without quasiparticles, because I think we do have quasiparticles in here. But I want to spend 1 minute at the very end to show you a bit how maybe we could experimentally move, or how we could think in directions where we might be able to get rid of them. So let's see. I want to acknowledge the people that actually did the work. So there's Marco Chunju and Karsten, our team at EPFL, and then now we move to Hamburg to the Max Planck for Structure and Dynamics of Matter. A lot of help came also from the group of Claudia Felser in Dresden, and our theory friends at the University of Zurich in the group of Titus Neupert were really critical in getting us there. So what is it? What do I want to talk about? I just flashed this real quick to remind you of what Stephen had already told you. So there's not much news about this. Cesium, vanadium, antimony is this Kagome material. Just to remind you, we have a charge density wave transition that sits at around 100 Kelvin. Then at some intermediate temperature, something happens. We're not, I would say, in agreement of what actually is happening there. But we do agree that at low temperature it goes superconducting again. And I just have a large list of things that have been somewhat talking points in the field. You'll find evidence for and against both of this. For example, we had a long discussion on time reversal symmetry breaking. Some shows in this direction, some doesn't. Inversion, some shows and some doesn't. We have nematicity and absence of nematicity and so on. So take it as a somewhat of a talking point of how this system unfolds very complex type of behavior. Since I'm an experimentalist, I want to talk briefly about how we actually do this, and I want to show you how the stuff actually looks like. Yes, please.
On the previous slide, you said Kerr.
Yes.
Does it occur at 30 to 35 Kelvin? Because what's the onset temperature of Kerr?
Oh, sorry, I put this in here. So Kerr has no onset temperature, right? So Haran showed that there is no Kerr at any temperature.
Right, so no Kerr.
No Kerr. Yeah, sorry. Again, this is not, sorry. In the framework of broken time reversal, Kerr adds a language here, and it says no, and μSR says yes.
Thanks for the
μSR sees it at 30 Kelvin. Yes, thank you, thank you. I don't want to add more confusion into what is definitely an already confusing field, so thank you. All right, so this is how this stuff actually looks like. These are crystals grown in self-flux, very similar to what Stephen told us or taught us how to do. These crystals are usually on the millimeter scale, but they're very thin platelets. They're very thin platelets, about 40 microns. They're also very, very soft. So even if you touch them with something very soft, like an eyelash, you can very easily bend them. So these crystals are somewhat mechanically hard to work with, and in particular, if you're not interested in the transport out of the plane of the system, it's very, very difficult because of the shape of these objects. And here we can use a technique that my group's really pushing forward based on focused ion beam machining. So we take these types of crystals and then we cut them into all sorts of shapes on the micrometer to mini micrometer type scale. And I just showed this as somewhat of a flash of things that is going on. So we can look into layered out-of-plane systems from a quantum transport perspective. We can do all types of three-dimensional structures out of materials. There's quite a bit of interest in topological metals or heavy fermions and so on. So this is really just to show you what you could do. Think of it as you take this crystal and you chop it into whatever shape you need for your experiment. And so this is what we did. We start with these crystals and then we started chopping, and it actually is very difficult. It turns out that it is so soft that whatever you do to it, you immediately bend it. We had to work for about 2 years to get the right recipe. And I want to show you how this works. So the purple blob in here is a cross-sectional slice of these very thin crystals. But to avoid it from bending or straining, we have to mount it onto a 20 nanometer thick silicon nitride membrane. But even that's too strong for this thing. So we have to drill holes and cut it into spring shapes to reduce the residual uniaxial pressure at low temperature to about 10 bars. So this essentially takes away all of the mismatch strain between the sample and the substrate. And now we can align this slice in all directions with the crystal as we want. So in particular, we can do out-of-plane transport experiments. So the white lines here, these represent the planes, the Kagome planes of this material. So we study the transport through a stack of these planes. And so I want to very briefly convince you of three things that you could figure out about the material when you do this. So I was lucky that I can skip some of the introduction so I can add the third part. All right. So the first one concerns the fact that 3D physics is very important in this material and how you could actually figure this out. And what you could now do is you could now measure magnetotransport as a function of temperature in all current and field directions. So you can apply the current in the plane, out of plane. You can put the field in the plane and out of the plane. Of course, always taking care that you're working in a transverse geometry, so full Lorentz force geometry. Then you would find these types of results. So for example, out of plane current, in plane field, out of plane current, the orthogonal in plane field, they essentially look the same. Magnetoresistance is on the order of 10, so it's large, but it's not infinitely large. If you apply an in-plane current, out-of-plane field, you see larger Shubnikov-de Haas oscillations at low temperatures. That's nice. It tells you that there is something two-dimensional about this system. But by and large, it's very, very similar. But the fourth quadrant is surprisingly different. And we had to do this quite a few times to first trust it and then understand it. So at high temperature, there's no measurable magnetoresistance whatsoever up to 18 Tesla, which I would call a very substantial field. But then just at the charge order temperature, magnetoresistance pops back up. And at low temperatures, it looks the same in all directions. Sorry? Okay. So if you were to plot just the magnetoresistance, so the resistance at 18 Tesla minus the resistance at 0 Tesla divided by 0 Tesla resistance, you would find that this particular configuration has no measurable effect on the 10 to the minus 6 scale up to the charge order transition where the signal explodes by orders of magnitude. And then at low temperatures, it's not isotropic, but actually quite similar. So how could one understand this type of physics? Now, the first thing that you could say is maybe it's dirty. Dirtiness on a semi-classical picture will, of course, remove your magnetoresistance because we know the semi-classical magnetoresistance scales with mu b, right? So this is, I think, quite unlikely that suddenly as a function of temperature, the material self-purifies. And it also would need to be highly directional because all other directions, they, well, don't have this type of effect, right? So what we propose and could corroborate with band structure calculations is that really what happens is a dimensionality change. So if you have an ideal two-dimensional metal, then there is no orbital magnetoresistance in this configuration. You apply an in-plane field, in-plane current, your states slide in the out-of-plane direction, so actually nothing happens to an orbital channel. You don't expect orbital magnetoresistance. So one way how you could get this is a zone folding at the charge density wave transition, so that at high temperature the system is really described by cylindrical Fermi surfaces, and well, as you go into the charge ordered state, they remain, but they refold, and you get small closed three-dimensional pockets. And as soon as these three-dimensional pockets appear, your magnetic field can backscatter and magnetoresistance comes back up. These pockets are, of course, very important for the physics of this material because they encase the Van Hove singularities, which we learned from Stephen are very, very critical for the models that we have about the correlated state. So the way you should think about this is that at the charge order, the material actually becomes three-dimensional. So we really have to think about three-dimensional physics in this material. As beautiful as the 2D Kagome plane and the 2D models really are, they will not capture what happens in this compound at low temperature. Okay, the second thing that is quite surprising, and is a very unique, I would say, electromagnetic response, concerns what Stephen alluded to a little bit in the switchable chiral transports. I want to tell you what this is and how we figured this out.
Philip, I'm sorry, just a quick question of clarification. So when you say that I is parallel to A, and B is parallel to AB, what does it mean?
90 degrees off in the plane.
Always 90?
Always 90 degrees, yes, full Lorentz force.
What do you see if our current is parallel to the field?
Longitudinal?
Yes, longitudinal.
Essentially nothing.
Okay, thank you.
Yeah, that's a good question. So I made sure that they're full Lorentz force so that you can really compare the 4 quadrants. That's right. Okay, electromagnetic chiral anisotropy. What is it? The idea is that if you have a conductor that breaks all mirror symmetries, you're allowed to have a field-induced diode as a nonlinear response of a conductor to current. And you could write this down as something like this delta R. So what is it? It's the difference of the resistance of the conductor at a given magnetic field and a given level of current, again, it's a nonlinear current phenomenon, to the same resistor at the same field, but negative polarity of the current. So it encodes a polarity dependence of your current in a finite magnetic field. And since this is a field-induced diode, you can of course also look at this as the generation of second harmonic signal if you apply an AC current to this problem. So this has been studied quite a bit in various types of materials. You can see it. Again, breaking mirror symmetries is the key part to this. So for example, you can take bismuth, which is a very soft metal, and you just twist it like this, and you introduce twist dislocations that have a preferred chirality. So you can observe it this way. You can look into chiral magnets, for example, helical type of magnets. They give you this type of scattering response, or tellurium is a very prominent material in which we all know that it consists essentially of chains that rotate. So this is it's a chiral compound, and it exists in left and right-handed copies of the material. The key point here is that in all of these cases that we have, it's set by the crystal structure. It's the atomic positions in the sample that give you what is the prefactor of this, right? Is it a left-handed or is it a right-handed object? And this is different in CVS, because the first thing that you should say is, what are you talking about? You need to break all the mirror planes, but this compound is centrosymmetric. So we have 3 mirror planes in the plane and perpendicular. Yeah.
Sorry, I want to understand what you mean by chiral. Does it mean that you broke the mirrors, but you still have inversion symmetry, or does it mean that you broke all mirrors and inversion?
That you break all mirror symmetries and inversion symmetry, that's right.
Okay.
So, in a non-magnetic system, right? So if it's a magnet and you have time reversal symmetry breaking, it's a different story, right? But here we're talking about a non-time reversal, because the question is, do you have a symmetry that maps current to minus current? So that's what you need to avoid, right? So, okay, at high temperature in this state, we can definitely not have this. So if it appears, it somehow tells us that whatever happens to the system actually breaks the symmetry of this, breaks these mirror symmetries. And one example of this has been already shown is, for example, this chiral charge density wave. And that could be a way of how an electronic order gives rise to chiral transport. Now that's a quite interesting idea, because if that's true, an electronic order you could much easier switch. So you could, for example, imagine that you get a field-induced diode where the forward direction you could somehow change with an electromagnetic stimulus. So that's actually the response function that we find in this, and that's a rather unique property. So how does this now work? So we have these little stacks, these freestanding suspended stacks I showed you. The planes are like this, so we're probing out of plane transport, right? And we now apply a magnetic field that's almost, but not exactly in the plane. So you can think of it as a very shallow angle. I'll tell you why this angle is important in a second. A very shallow angle, and then we look at the resistance in the out-of-plane direction of this thing. And what we find is that indeed there's a very strong generation of second harmonic as that grows with applied magnetic field at low temperatures. It approximately follows a B-cube law, which we actually understand. This is just part of the magnetoresistance of the material. It doesn't exist for out-of-plane fields, or essentially any other fields, except for fields very, very close to the Kagome plane. This is a critical point. I'll show you the field dependence in a second. So the main point here is that even though this thing looks mirror symmetry breaking, it does show second harmonic generation. Yes?
Quick question, has that data been anti-symmetrized with field?
No, this is raw data.
Okay.
You can actually see it by eye, because the black line, I hate anti-symmetrization. The black line here is an actual fit to B cube, and there's a difference here that you don't find here. It's really B cube. Okay, so Yes, but thank you for this question because I really hate it. But what you have to do to understand this in terms of actual magneto-chiral transport, and you want to compare this to the other materials, like for example this twisted bismuth rod, then you have to really take care of the very large magnetoresistance. So you have to recompute this in chiral conductivity. So what I showed you before was delta R. Let's look at delta sigma. And delta sigma is much more insightful, because regardless of the field angle you put close to the Kagome plane, you find that it has the same slope until the field crosses the Kagome plane, at which it suddenly jumps to a slope to the opposite slope, right? So if you just plot the slope, it has a negative value once your magnetic field is on that side of the Kagome planes. Then when it comes to exactly zero, it immediately flips, and it has now a positive sign. And so that means that the chirality of this object is flipped, is switched, and it follows the sign of the out-of-plane field. So that's the key observation here. By changing the magnetic field direction, you can turn the material from a left-handed to a right-handed material. So if we want to understand this microscopically, you shouldn't ask someone like me, because I do transport, right? I have no local probes, but we could speculate with a cheerful spirit, and we could come up with a model that I think should be tested. I'm not saying that this is proven. I'm saying this is an idea that's compatible with our results. In that case, a transition from left to right-handed material occurs with out-of-plane field. So at very high magnetic fields out of plane, you have a monochiral thing. So you don't have a chiral scattering center. As you bring this polarizing field down, domains of opposite chirality start to appear. These are, of course, ideal scattering centers. You have a sea of left-handed with right-handed islands. So you see a very strong scattering right as the field comes close to the Kagome planes. But when it is in the Kagome planes, well, essentially there's no more polarization, so you just have a net balance. Then you see the opposite thing on the other side. This is a picture. I think definitely we'll need local probes in field to do this, but it's a picture that will be compatible with what we see. Okay, I want to just briefly mention something else, namely that strain is extremely important in this, and I think this is part of, if not the main source, of the controversies in this field. And the answer is the question is the following. Suppose you have this Kagome net, right? And you now apply some in-plane strain. Of course, you break the rotational symmetry of the object, right? But we could do this in an experiment. So now we can make these kind of slices with a hexagon in the plane, like this. Okay, so this is not an out-of-plane slab anymore. This is in the plane of the Kagome. So if you look very closely, you will find that this is about a 20 micron wide, perfect hexagon that's aligned with 0.1 degrees with respect to the Kagome unit cells. And you have at the corners little contacts, all of this suspended with our spring magic so that it really does not distort whatsoever as you cool it down. So you can probe what is there an intrinsic symmetry breaking and transport, yes or no? And the answer is no. In none of our samples we could find this. So if you measure resistance as a function of temperature in all these samples, for all these configurations of current, you find the exact same result at any temperature. So that's good. Well, it doesn't agree with some claims of nematicity in the compound, but that's okay. We don't see any of this. We can apply strain by not making the springs, so we pull on one direction and voila, it's there. Two of the directions are identical and the third one pops up. So that's not surprising. You break the symmetry, symmetry is broken. What is surprising is that if you have no strain, but you apply a very strong out-of-plane field, you get the same effect. So an out-of-plane magnetic field induces, at low temperatures, an in-plane anisotropy. Okay? So somehow strain along a Kagome lattice vector does the same as an out-of-plane field. It's a piezomagnetic type of response. And so the idea that we try to propose is that the material itself is isotropic at any temperature. But if you do something to it, like a little bit of strain, a little bit of magnetic field, a little bit of both, you throw it out into an anisotropic plane, it picks a preferred direction, as you could see, for example, in the unidirectional orders that SDM gives you. Okay, and with that, I would like just to spend 20 seconds to go towards the non-quasi-particle type of things, if I can. Just 20 seconds. So, it's a complete break, it's an idea, but I thought this would be a great place to promote this idea. The idea is very simple. We love in the design of quantum materials to stack different things. So, for example, the LAO-STO interface, you could think of taking two things, you look at the interfaces of these things and you find new types of responses. It's a traditional way of how we do stuff. Then if we think in our community, we could think of correlated systems which with the application of some tuning parameter can be changed to be in different phases. For example, I can take an antiferromagnet and tune it into a superconductor, tune it into a heavy fermion state. So what we're currently doing is we try to engineer this, and I just stole this from a talk, so forget the advertisement part, to engineer this in terms of phases. Could you imagine to take a single crystal and you apply a gradient of the tuning parameter that's so strong that you bring two phases within the same material into contact? And then what happens at the interface? Of course, this would be very interesting in terms of, for example, quantum criticality, that you could say apply a strain gradient, which is mostly what we do, a very, very extreme strain gradient, so that you interface between these two regions of the crystal, a manifold where you have right your quantum critical point. So this is something I've just wanted to throw out. Experiments like this will come out. This actually works beautifully. And with that, I want to conclude. If you want to talk about this or anything else, I'm more than happy to, because I would like people to think more about new materials under extreme gradients, and I thank you for your attention.
Hi, Philip. Can you go back to that slide 11? It's back to my question. I'm still a bit confused.
Slide 11, fantastic. Good.
I think so. Plus or minus 1.
Okay.
Yes. So what you're referring here, right, is breaking the diagonal and vertical mirrors.
Yes.
But that doesn't break the horizontal mirrors, so inversion symmetry is preserved.
Okay. Yes.
So I wouldn't call it chiral. People would call this ferroaxial or something like that, but that's different than chiral. It preserves inversion symmetry.
Yes, you're absolutely 100% correct. However, it depends on which direction of crystal you apply the current, right?
I agree.
In a chiral material, you can just do it in any direction.
Right.
You're right.
But just for the language.
Okay, you're right.
But then what you're describing is precisely the piezomagnetism that, we also talk in that paper, and you also talk here, and right? But that is then, you're seeing that directly in transport. I would say that this is evidence that you're breaking time reversal. You can't have piezomagnetism unless you break time reversal symmetry.
Not to linear order. You could think of some higher order terms.
But then it's not piezomagnetism. You wouldn't shift with B. That would be magnetostriction, not piezomagnetism.
I agree.
I know you don't want to say that, but I think your data is directly supporting the STM and the idea that you have time reversal symmetry. And it also is consistent with Aaron's data of lacking inversion, lacking
magnetization. Yeah,
when you apply strain, as you said, then he should see something.
I agree. I fully agree with this. All I'm trying to say is that I think in this field there's a lot of extrapolation of things to making very strong statements, and I try to be as careful as possible to not contribute to that, right? But I think your interpretation is right. I personally believe, but we're not in church, that this is true. But I could easily also consider some, and then my statement of piezomagnetism would be wrong, right? But I could easily imagine some higher order things where you could wiggle. Exactly. Then it's not piezomagnetism. I agree with you, Raphael, 100%.
You can make strong statements when you talk about symmetries. So.
Yes, exactly.
Okay.
So, Philip, very nice talk. So, 2 questions, very quick. First, I didn't get, do you make a connection between the third part and the second part of your talk, in the sense that since magnetic field somehow removes the inversion center in plane, so you didn't mention, you were thinking about how chirality can be induced by a magnetic field just by moving atoms. Isn't that the right way to understand?
Okay, so the difference between the second and the third part is the direction of the magnetic field. So to see the chiral transport, you need to have a very strong in-plane magnetic field, which essentially is a probing field perpendicular to your direction, and a little bit of poling field, right? So it's 89 degrees. The switching, the opening of the piezo is purely along the C direction.
Yeah, but
So it's 90 degrees rotated magnetic field, which is important because you're a different symmetry.
yes, but you need a small magnetic field, and you had, as soon as you begin to say that putting a magnetic field with some z-axis component
Yeah.
has some, effect, then it becomes less mysterious. Because the question was, how come? Okay, my second question,
I agree.
very quick
That
question.
I agree with, yeah.
So you give conductivity in volt -1. Why not in Siemens? Because then I can compare your chirality with other systems like tellurium, how big it is.
Yes.
Can you compare?
Yes. The conductivity is actually higher than that of tellurium. The reason for why this is in inverse volt is, and we had long discussions about these, is essentially because it comes from the inversion of the resistivity tensor in the because it's a delta sigma, and the question is, do you normalize delta sigma by sigma naught or not? In which case it would be a unitless quantity.
So how much is your gamma compared to tellurium?
This is a difficult question because the gamma in tellurium has a linear dependence, right? So it goes as B. We see B cube, and that's coming in because of the determinant, because of our B linear magnetoresistance. But so it's a field-dependent gamma if you want. But if you just take it at face value, it's about 3 orders of magnitude smaller than tellurium.
Thank you.
But it's field-dependent, so.
Other questions? No? Then let's thank Philip.
Well, thank you.
And I think we need to be back here in a half hour.